Okay, section 2.4, we're going to talk about exponential functions and logarithmic functions. So I don't know why this is in chapter 2. Shouldn't it not have been in chapter 1, which was a review of all of our pre-calculus? Have you studied exponential and log functions in algebra or pre-calculus before? So I don't know why it's in this section. It's almost like the author forgot and said, oh yeah, well, let's put it right here. So an exponential function base b looks like this. B's any number, well, kind of. It's pretty boring if b is 1, because 1 to any power is 1. And we don't want b to be negative because then it flops back and forth. So let's make b any number bigger than 0. 0 to a power is boring, but not equal to 1. So we'll only talk about bases that are positive. So they're kind of backwards from polynomial functions. Polynomials had the variable as the base and the number as the exponent. You swap places and you've got an exponential function. And when we look at the graphs of these, you'll see some common traits. So I wanted you to graph maybe 3 of them. The first one I want you to graph is f of x is equal to 2 to the x. So 2 is my base here. And we'll graph it by plotting some points. So let's just make a little chart here. So I'll start with 0, 1, 2, and then we'll plot -1 and -2. All right, I'm putting 0 in for x, and I get 2 to the 0. Who knows what 2 to the 0 means? 2 to the 0 is 1. Any number to the 0 power is 1. All right, what about the next one? 2 to the 1. 2 to the 2 is 4. What's 2 cubed? 8. This is going to be a doubling function. It doubles the previous entry. When I put a -1 in there, what does 2 to the -1 mean? What's a negative exponent mean? 1 over, right? You flip the base and make the power positive. So 2 to the -1 is a half. What do you think 2 to the -2 will be? 1/4. Are there any powers that I could put in there so that this thing has a value of 0? 2 to a power is 0. Wasn't meant to be a stumper. 2 to the x is always positive. B to the x is always positive. Okay, so it's going to look something like this. Here's the graph. I can put any number in I want up here. And I'm going to get these numbers out. I get 0, 1. I get 1, 2, 2, 4. Now remember 3, 8 would have been way up there. -1, a half, and -2, a fourth. So I'm going to be able to get numbers real close to 0, but not equal to 0. And then these zip up real quick. Things double as I move each unit to the right. The y units are double what they were before. Okay. All right, so let's keep in mind some of the things that we pointed out here, that our exponential function to the 0 power is going to give us 1, and that our y values are never going to be 0, and they're never going to be negative. And I can plug in any value of x. At the bottom of the page, I'm going to list those as some of the properties of exponential functions. The next one I want to graph is 1/2 to the x. So my base now is a half. But you should get used to seeing it as 2 to the minus x, because again, a negative power means to flip the base. I'm going to plot the same numbers. Plot 0, 1, 2, -1, -2. When I plot 0, I get 1/2 to the 0, and as before, any number to the 0 power is 1. Then I get 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 cubed will be 1/8. So I'll be able to make the y values real small as I march out the positive x-axis. When I put a negative power in here, I can look at it this way, that it changes the sign and I get a +2 here, and then the 2 squared or 4 right there. So it's going to take that and flip it about the y-axis and give us values here, 0, 1 as before, but now 1, 1/2, 2, 1/4, and they get close to the x-axis there. -1 goes up to 2, -2 goes up to 4. So we've got something going on here. Never going to be 0, goes through 0, 1, and is never negative. In the first example, we've got a doubling function, and this one cuts things in half. This is an example of a growth curve. We're going to talk about exponential growth. Have you heard things grow exponentially? They grow as a multiple of the previous amount. And this is exponential decay. This is a decay curve. This is often used in some sort of population biology. You stick a petri dish of gooey stuff in the closet. What are gooey stuff called in biology? Microbiologists. Cells. Put some of these cells in the closet, and they'll start multiplying, and then they multiply based upon how many was there the previous time period. So they grow exponentially. Things that decay exponentially might be like radioactive waste. You have a quantity of kryptonite, my favorite radioactive material, and it decays at a certain rate, then after that time period, half of that is left or a part of it is left and so on. So it decays according to amount previous there. There is a number that is often used as the base when we talk about exponential growth, and it is the number E. Do you have an approximation for how big E is? 2 point something, 2.71, blah, blah, blah. It's an irrational number, much like pi is an irrational number, meaning that it is a non-repeating, non-terminating decimal. So we use a symbol for it. Another example of an irrational number is square root of 2. We write that symbolically, where square root of 2 is 1.14, blah, 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 blah. Goes on forever. So if E is used as the base, yes, sir?
How did we get E?
E came from the famous mathematician Euler, who was studying population biology back in the days before computers and calculators and things. He was developing these population models, and in his population models, he had this type of expression always show up, and he had to evaluate that as n gets bigger and bigger and bigger and bigger. And he was able to determine that it becomes constant. And he named that constant E. Right, as n gets bigger and bigger and bigger, this thing behaves like 2.718, and there's more back there. How he did such finite calculations, I don't know, but he realized that he's getting this irrational number, E, because it's Euler's number. So you'll see this expression again later on when we do some more limits, and this number E shows up. So we call it E. When E is used as the base of an exponential function, we have something called the natural exponential function. It's called the natural exponential function because all exponential functions can be written as powers on E. And when we graph this thing, we'll just approximate E to be 3. We can't graph something so fine as 2.718. So if E is equal to 3, then we've got something that nearly triples with each increase in X. So its graph is going to look exactly like the graph of 2 to the X, just at a different scale. It's going to go through 0, 1, but then it goes through the ordered pair 1E and 2E squared and negative 1, 1 over E, and so on. But it is a growth curve. And so when you see the number E, think of it as being not quite 3. So now let's list our observations at the bottom here, where it says, list the properties of the exponential function. Properties of f of x is equal to some number to the x. So the first thing that we observe is that b to the 0 power is 1. So the y-intercept is always the ordered pair 0, 1. The second thing is that if b is bigger than 1, we have a growth curve. If b is a fraction between 0 and 1, we'll have a decay curve. But in either case, this graph never hits the x-axis, never dips below the x-axis. That means its range is the set of all positive y values. And I can put any number I want for the exponent, not just integer values. I can put irrational numbers there as well. So that says the domain is the set of all real numbers. So we have the domain is the set of all real numbers. And its range is the set of all positive y values. It will never equal 0. Never, never, never. They're continuous functions and they're one-to-one. So it's going to have an inverse. And we'll get to that. They're continuous for all x. And are one-to-one. So F inverse will exist. And these things, here's another way of saying they're one-to-one. They're one-to-one means that if b to 1 power, let's call it m, is equal to b to the other power n, then the only way that can happen is if m and n are the same thing. That's what we mean to one-to-one. They're only equal if the exponents are equal. Then some other things follow the properties of working with exponents. Earlier, we said that, let me just write that here, that they obey the laws of exponents. That b to the minus x is the same as 1 over b to the x, and vice versa. If the negative exponent is in the denominator, you move that base to the numerator and change the sign of the exponent. What do you get, for instance, if you multiply the polynomial x to the 5th with x squared? X to the 5th times x squared. You get x to the 7th. When you multiply like bases, you add exponents. So I'm going to write that as b to the n times b to the m. It can be written as a single function where I add the powers. What happens if you raise a power to a power? What is x to the 5th quantity squared? It's x to the 10th. You multiply exponents when you raise a power to a power. So b to the n as a quantity raised to the mth power is b to the n times m power. When is it that you subtract exponents? When you divide. B to the n divided by b to the m is b to the n minus m power. Those properties and our definitions up there allow us to solve exponential equations. So let's look at solving some exponential equations. Have I told you anything you don't know yet? Just a little refresher. Okay, so we use these ideas to solve exponential equations. You mainly use this one, that if two exponential functions of the same base are equal to each other, then the powers are equal to each other. And so I'm going to use that here. The first one says find the value of x so that 2 to the x plus 1 is equal to 16. So we can almost do this mentally. 2 to what power is 16? 2 to the 4. So what does x have to be? So x has to be 3. But I'm going to write it like this. I know 16 is 2 to the 4th. And now I have this statement that says all I've got to do now is set the two exponents equal to one another. That x plus 1 is equal to 4. So x is 3, just like you said. So if it's not so obvious what the power is going to be, this one was obvious because it was a nice whole number. Let's try to see if we can write both sides of the equation as powers on the same base. And so my next example, I have 1/3 times 3 to the x is equal to 9 to the x. I'm going to rewrite all three of these terms as 3 to a power. I'm going to write 1/3 is 3 to the negative 1. And I can just write that one again. And then 9 itself is 3 squared. So I'm going to write this as 3 to the negative 1 times 3 to the x. 9 is 3 squared, and then raise that to the x. Now combine where you can using those properties of exponents. When you multiply like bases, you add the exponents. So this can be written as 3 to the negative 1 plus x. When you raise a power to a power, you multiply exponents. So the right-hand side can be written as 3 to the 2 times x. And now we have the same situation that we had before. Two exponential functions of the same base are equal, only if the powers are equal. So now we can make the statement that -1 plus x is equal to 2x, and we solve for x. I guess I just subtract x from both sides. And we have it, -1 is x. So let's try another one. Number 3. I have 4 to the 10 minus x is equal to 8x. Well, 8's not a power of 4, is it? But both of these can be written as powers of the same base. What base? Base 2. Let's replace the 4 with 2 squared, replace the 8 with 2 cubed. And use the property that when you raise a power to a power, you multiply exponents. So the left-hand side, I'll have 2 to the 20 minus 2x. Distribute the 2 all the way through there. So 2 raised to the 20 minus 2x. And then over here, raise a power to a power by multiplying, and you get 2 to the 3x. So with a couple of steps, we successfully wrote both sides in terms of the same base. The rest is just setting the 2 exponents equal to one another. And solve for x. Add the 2x to both sides, and I get 20 is equal to 5x. Divide by 5, and we get x is 4. Easy enough? Well, you like to think so. And I'm going to whip out one like the next one. Three to the x is 5. Neither 3 nor 5 can be written in terms of powers of the same number, and they're both prime. So they don't have any factors other than themselves. But I know there's one and only one solution to this equation, because I know what y is equal to 3 to the x looks like. There's 3 to the x. And so here's y is 5. Here is the x value that I'm looking for. But I can't find it algebraically doing the same steps that I did before, but I know it's there. And here's where the fact that this function is one-to-one. All one-to-one functions have an inverse. That if this x goes to that y, then the inverse function is going to take that y back to that x. I don't know how to find it algebraically. How do we normally find the inverse of a function? If I give you y is equal to blah, 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 and I say find the inverse of it. Interchange x with y and solve for the new y. Well, here we go. I'm going to take y is equal to b to the x, right? So b to the x is a one-to-one function. I'm just going to use a b instead of a 3. I know it has an inverse, so I swap x with y. And now I got to solve for y. Now's where I'm stuck. So we're not really stuck because this is math. We can just make a definition. And this value of y is called the logarithm base b of x. The exponent that goes on b to give you that number over there, that 5, is going to be called the logarithm base 3 of 5. This exponent is the logarithm base 3 of the number 5. Whatever the power is here. So to keep you from getting mixed up with u's and x's, I'm going to go this way. I'm going to say that the logarithm base b of a value v is an exponent u if and only if b raised to the u is equal to that value. There's my definition of the logarithm base b. Logarithm finds an exponent. This number here is that exponent. Or in other words, it says b raised to the logarithm base b of that value v is v. These are one-to-one functions, so that if I had a logarithm of an exponential function, I'm going to now put, instead of the v here, I'm going to put the b to the u there. It says that the logarithm base b of b to the u is equal to u. Those are all of our one-to-one relationships. This one says that f of f inverse of an input is that input, and this one goes the other way. That's what those two say. But all I did is I substituted the u out for the log base b of v, and then I substituted the v out for b to the u. As a function, let me write it down in terms of function notation. Where can I put it? I can put it over here. All right, f of x is equal to the logarithm base b, b I said. This base is the same base that we had a minute ago in the exponential function. It can't be negative and it can't be 1. B is positive and b is not equal to 1. These numbers right here are the y values that we had generated by the exponential function. And remember that all of those y values were strictly above the y-axis. That says that the domain of this function is all x's strictly positive. And all these y values here, where the x's for the exponential function, they can be any number. And so the range is going to be any number. I'll write that down in a minute. But let's sketch a graph of this by doing our little flipping thing. Let me draw the graph of the exponential function with b bigger than 1. So that is f of x is equal to b to the x with b bigger than 1. And it goes through 0, 1. Its inverse is going to be, let's just call it g of x. Let me call that one g so that I can keep going with the f here. It's a pretty color red, isn't it? Its function, the inverse of that, is that guy. It takes all the ordered pairs on here and flips them. Or it allows us to sketch the graph by flipping that about the line y is equal to x. So it's going to take the ordered pair 0, 1 and give me the ordered pair 1, 0. And then suppose I have a point here and I rotate that about that line. And it should go about right there. If I take this about that line, it's going to go about right there. So here's the graph of a logarithm. It's a slow growing thing. The exponential function hugs the negative x-axis. The log function hugs the negative y-axis. Passes through 1, 0, and then it grows slowly as opposed to quickly. If I do the inverse of the decay function, then the graph is going to look like this. Here's the decay function in red. That's the exponential function. F of x is b to the x of b is smaller than 1. So the log function is going to do that little flipping thing. Here's the line y is equal to x. So flip that point here. It's going to, this one hugs the positive x-axis, so these will flip up to here, like that. And these values will flip down here like that. So here's the log function, base b of x, if b is smaller than 1. So I'm going to write the properties later. So let me sketch the graph of the log base 2 of x and the log base 1/2 of x. Okay, so all I got to do, if I want to get the graph of the log base 2 of x, I just look at the graph of the log base 1/2 of x, I'm sorry, 2 to the x, and then I have it, right? And if this is the log base 1/2 of x, oops, that's exponential function. So I got my functions backwards. This one's 1/2 to the x. And then this one would be the log base 1/2 of x in black. You bring your black and red pens with you? If the base is a number bigger than 1, you're going to have a mimic of that black graph over there, a slow growing graph that lies strictly to the right of the x-axis. If you have a base smaller than 1, you'll have still something that decays, but decays real slow and goes through 0, 1, lies strictly to the right of the y-axis. We'll list those as properties later on. Now, a minute ago, I got as the value of the exponent log base 3 of 5. Right, so log base 3 of 5 is some irrational number. That acts as the exponent on 3 to give me the number 5. Gives me this exponent right here. But that's not very useful, because what if I wanted to approximate that as a decimal? Well, back in my day, our textbooks used to have tables of logarithms of different bases. So what we would do is we'd find the column for log base 3, and then I'd read down this column for 5, and there's like a 4-place decimal approximation. That was before all these super-duper calculators. Now we can do this on our calculator, except if you look on your calculator, you don't have a log base 3 button. You have 2 different logarithms on your calculator. The one that just says LOG and the one that says LN. Those are our 2 special logarithms. The one that says LOG is a logarithm base 10, and it computes the exponents that go on the number 10. That LN logarithm is called the natural logarithm, and it's a logarithm base E, called the natural logarithm, and it gives us powers that belong on E. to give us numbers. So our two special logarithms you see this logarithm?
No, it's just
That's a logarithm base 10. So the logarithm base 10 of a value v is an exponent u if and only if 10 raised to the u is that value v. So this is a logarithm base 10. All I did was mimic that. B is 10. When B is 10, we don't write it, much like we don't write a 2 when we talk about square roots. Then when you see this logarithm, that's a logarithm base e. The logarithm base v is an exponent, a logarithm, natural logarithm of v is an exponent u if and only if e to the u is that value v. And we don't need log tables anymore because our calculator has this conversion built into it. The logarithm of any other base can be written in terms of any other logarithm, preferably a log base 10 or a natural logarithm. Here's the conversion factor. Logarithm base b of any number can be written in terms of, say, a log base 10. It would be the log base 10 of that number divided by the log base 10 of b, whatever the base was. I prefer to use a natural logarithm. It's one less letter for me to write. So I can write this conversion factor also in terms of a natural logarithm. If for some goofy reason I wanted to use a log base 2, I could also write this in terms of a log base 2. It's an easy formula to remember because you pick your log base that you want and put this part in the numerator and then that part in the denominator. So let's get a decimal approximation for the log base 3 of 5. If you have your calculator or even a phone calculator, you can pull it out and compute this. So let's get a decimal for this. The log base 3 of 5 will be the natural log of 5 divided by the natural log of 3. Let's see where I put my phone. All right, so let's see, the natural log of 5. Oops, gotta go the other way, clear. Natural log of 5 divided by the natural log of 3. Excuse me, you get something like that? And now just to verify that, I said that that's the power that goes on 3 to get 5. So let's now to hit the 3 to the x button or hit our exponential button. So let's go 3. I don't know how to do it. 3, back up. I don't know how to do that on here. Clear. 3 raised to the, nope, that's not what I want to do. Clear. 3 raised to the, I just put these 1.4649, blah, blah, blah. Sure enough, I get 5, right? If you keep all your decimals, that'll get you to 5. Right? So it's an irrational number. Yes, sir.
Oh, I don't know if you have a graphing calculator, you can actually put in log base 3.
Yeah, sure is. There it is right there. That's no fun. We don't use calculators in this class, so it doesn't matter. Now, if you wanted to enter something like this on web work, you'll have to use a logarithm base 10 or a logarithm base E. I don't think web work is going to recognize the other logarithms. Okay. Okay, so we've looked at the graphs, and I want to now do some calculating. So pay attention to this definition. We're going to calculate some common logarithms without using our calculator. That red shows up. Okay, I'm going to stick with the red. I'm kind of feeling in a red mood today. So we're going to calculate. So when you see log base 3 of 81, read it like this. The log base 3 of 81 is an exponent. You're asking yourself, 3 to what power is 81? So start computing powers of 3 until you find what power it should be. 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9.
Should be to the 4th, right?
To the 4th power. 3 to the 4th is the same as 9 times 9. So the log base 3 of 81 is 4, because 3 to the 4th is 81. All right, next one. That's visible. Yeah, okay. The logarithm base 2 of 1/8 minus the logarithm base 4 of 2. So let's do these separately. The first one is seeking an exponent that goes on 2, so that 2 to that power is 1/8. Well, you see that fraction. You know you're going to need to get a negative power so that we flip our base, right? So the power is negative. Which one is it? It is -3. 2 to the -3 is the same as 1/2 cubed, which is 1/8. Now the next one. So this is -3. Go ahead and put that here. The next one, we're looking for a power that goes on 4 to give us 2. Not a -2, because a negative flips the base. But do you recognize that the square root of 4 is 2? What power is the square root? 1/2. 4 to the 1/2 is the same as the square root of 4, which is 2. So this number is representing a half. And so our final answer as our evaluate is -3.5, which is -7/2. Okay. So the square root is a 1/2 power. A cube root is what kind of power? 1/3. So a lot of times if you had to enter a cube root in web work, you'll use a 1/3 power, right? Cube root of a number means that to the 1/3 power. So in web work, you'd write it like this: a raised to the 1 divided by 3. Getting the hang of web work yet? You still cussing it? Just a nudge. Just a nudge. Okay, the next example, we're computing in log base 10 because I don't have a base written. And it looks like this. Number 3, I'm going to multiply the log base 10 of 1,000 with the log base 10 of 0.01, 1 over 100. So this first one is asking for a power that goes on 10 to give me 1,000. What power is that? That is 3. 10 cubed is 1,000. The second number is asking for a power that goes on 10 to give us that. But if you read that, that's the same as 1 over 100. So if you're into fractions, do what we did over here. 100 is 10 squared, so 1 over 100 is 10 to the negative 2. So this is negative 2. 3 times negative 2 gives us negative 6. You guys ever hear of a slide rule? Has anybody ever worked with a slide rule? They should do that. They should do some sort of historical engineering class. You know, engineers used to have to do calculations with this thing called a slide rule, which is kind of like a movable ruler. And what it actually was something that computed logarithms. Logarithms help us tame down big numbers. So instead of looking at 1,000, we deal with the number 3. Or if we had 1,000,000, we'd use the number 6 because that's the power on 10. And so they were able to quickly do these multiplications by thinking of things in scientific notation, 10 to a power times 10 to a power. And this little slide rule would do that for them. Any engineer who was probably my age, I like 100 years old, would have a slide rule laying around. Okay, the next one, we are to compute the natural log of e to the 6th. But look at what we're doing. The natural log of a value, so here my value is e to the 6th, is an exponent. The natural log of e to the 6th is an exponent that goes on e to give me e to the 6th. So what am I looking at? It's just 6. Now, the reason that this is just 6 is that these functions are inverses of one another. Remember that I wrote that a raised to the logarithm base a of any number is that number. And if I had it the other way, a logarithm base e of e to a power is always the power. So now I've got a list the basic properties of logarithms as my next task. That's going to be in here. I'm going to move this to the left a wee bit. Right in that big blank space. Maybe. There we go. Here's where we'll write it. Some basic properties of log functions. So first we'll talk about the function. We'll talk about it in function form. F of x is equal to a log base b of x, or base 10, or a natural logarithm. All of these have the properties that any logarithm of 1 is going to be 0. And that's because these are inverses of exponential functions. All of our exponential functions, remember, pass through the y-axis at 0, 1. All of our log functions have an x-intercept of 1, 0. When the input is 1, the output is 0. So that says that all exponential functions pass through the ordered pair, x is 1, y is 0. These things have as their domain all positive values of x. There's no such thing as a log of 0. There's no such thing as the log of a negative number. Because remember, these have as their domain the set that was the range of the exponential functions. So we're going to say that the domain of any logarithm is x strictly positive, but the range can be any number. If the base is bigger than 1, then these things have a vertical asymptote of the negative y-axis. And if the base is bigger than 1, then the vertical asymptote shows up at the positive y-axis. But the y-axis itself is a vertical asymptote. I'll write down the inverse properties in this way. Let's see if you recognize them. The natural log of e and the logarithm of 10 and the log base b of whatever b is all have the same value. Do you know what that value is? Those all have a value of 1. Because it gives us the exponent that goes on the base to give us those numbers. B to the 1 is B, 10 to the 1 is 10, E to the 1 is E. So we can write the more general version of this as the natural log of E to a power is whatever the power is. The log base 10 of 10 to a power is whatever that power is. And the logarithm base B of b to a power is whatever that power is. And then finally, a logarithm is an exponent. So we combine logarithms using the properties of exponents. When you raise a power to a power, you multiply exponents. When you multiply like bases, you add exponents. And when you divide like bases, you subtract exponents. So these 3 properties now, I'll just write in terms of a natural log, but are true for all logarithms. The natural log of a times a power is the natural log of a to a power. When you raise a power to a power, you multiply exponents. The natural log of a plus the natural log of b is the natural log of a times b. When you multiply like bases, you add exponents. And similarly, when you divide like bases, you subtract exponents. So these are the algebraic properties of logarithms that mimic the algebraic properties of exponents, and I'll use those next time to solve some log equations. So that ends us week number 3. All good? Okay, I think I've got some more problems that you might be able to get started on those, just so that you don't have an idle weekend. All right, let's pull it down. Yes, do you have any questions? I'll shut off the recording.
step, watch step, watch step.